What actually goes on in a computer to solve a simple math problem? How do we go from numbers and symbols to a final result? Well, let's see. Let's take 4 plus 2 times 3 minus 10 divided by 2. To start with, computers, a lot like humans, break down larger problems into smaller parts. In computer jargon, these are called instructions. Think of these like a sort of problem-solving recipe with simple, easy-to-follow steps. So our first step to a solution is to write our computer some instructions. Let's start by breaking down our expression into 4 simpler binary operations. X equals 10 divided by 2, y equals 2 times 3, y equals 4 plus y, and z equals y minus x. Solve for z, and we know the answer. Next up, we'll need to write these in a way that our computer can understand them. To start with, we'll do some simple rewriting and make these instructions look a lot more like functions of 2 arguments. And with a bit more abbreviation, we get something that looks a lot like a low-level computer program, something programmers would actually call assembly. Well, actually not quite, we still have these equal signs. Unfortunately, computers aren't really smart enough to understand arbitrary variables like x, y, and z. To decide where we actually want intermediate values to go, we'll need a short digression into memory. Memory is a catch-all term in computing for anything that a computer can read data from or write data to. There are many different kinds of memory, all with different speed and size trade-offs, but here are a few of the most common. The fastest bits of memory in a computer are called registers. These live right next to the processor or brain of the computer. They keep whatever the processor is thinking about at this moment, like if we need to add 2 numbers, compare 2 numbers, multiply 2 numbers, they'll both be in registers. Think about it as working memory. We can't keep a lot of data in registers, but we have quick access to what's in there. Next up in the hierarchy is random access memory, or RAM. Orders of magnitude slower than registers, but stores orders of magnitude more data, though random access refers to being able to read and write RAM in any order you choose. It isn't quite long-term memory, but it's more akin to something in between short-term and long-term. Beyond registers and RAM, there are other forms of memory which aren't really relevant to our current example, but just know that as we go down our hierarchy, things get a lot slower and a lot bigger with each jump. So back to our instructions. Now that we know where to put them, let's have our computer stick our intermediate values in registers. We'll rather arbitrarily call them R1 and R2 for the sake of convenience. And again, some quick reformatting and we have our final assembly code. Let's do a quick step through to make sure that everything is correct. We divide 10 by 2 and put the result in R1, multiply 2 by 3 and put the result in R2, add 4 in R2 and put the result in R2, and subtract R1 from R2 and put the result in R2. And our answer is 5, which is right. So how do we get this on our computer? Well, we need to get the instructions into RAM first, but there's actually yet another step even before that called an assembler. A computer program which takes our computer program, written in assembly, and turns it into binary code that the computer can interpret. An assembler uses something called an instruction set architecture, or ISA, to convert programs into binary. An ISA is made up of hundreds or thousands of rules defining how every unique operation a processor is capable of is encoded in a way that the computer can understand. For our case, we'll define our own ISA. We'll just give each instruction and register a unique number. So, rather arbitrarily, let's make addition 0, subtraction 1, multiplication 2, division 3, and then R1 0 and R2 1. Do some quick encoding according to our tables and we're actually almost ready to go. Just a little more housekeeping. Since all we have here are numbers, our computer won't be able to tell for each of these arguments whether we mean each as a register or a literal number. To help our processor out, we'll use something called a flag, a value that's either 0 or 1 to indicate for each argument if it's a register or a number. So for each instruction we have 2 extra numbers. The first one is 1 if the first argument is in a register, and the second one is 1 if the second argument is in a register. And now with that cleared away, we're golden. We have our instructions, but actually one last thing. They're written in our normal base 10 number system, decimal, and our computer will read them in base 2, better known as binary. To understand the difference, we'll need a short digression into binary. Humans read numbers in base 10. Take the number 17. From left to right, we have a ones place and a tens place. Each time you go left, the value of the digit increases by 1 power of 10. To construct the number, we'll take the value of each digit and multiply it by the value of its place. Easy enough. Binary numbers operate on the exact same principle, but they use 2's instead of 10's. Let's take 17 again, but represented in binary. 10001. This time we have a 1's place, 2's place, 4's place, 8's place, and 16's place. Looks confusing, but the process is actually the same. Take our binary number, multiply the value of each digit by the value of its place, and 17. To convert a decimal number to binary, there are quite a few methods, but here's a quick way. Take 140. Start with the highest power of 2 that's less than or equal to our number, in this case 2 to the 7 or 128. Go down the list of powers of 2, highest to lowest, and if our number is greater than the value of that power of 2, subtract that power and put a 1 in that place, otherwise put a 0. 140 minus 128 is 12, so put a 1 in the 128's place, then all zeros until we get to the 8's place, and then another 1 in the 4's place, and we fit 0. Fill the rest in with zeros and we have our number in binary. Now I won't bore you with doing this for all of our instructions, so here's the binary. And some more important terminology. Each one of those 1s and 0s is called a bit, short for a binary digit. Put 8 of them together and that's called a byte. Bytes are sort of a universal grouping for binary data, and this is important because the last thing we need to do to our instructions before we can load them up into RAM and tell the processor to do what they say is to pad them out or make them a consistent length in bytes. Usually our instruction set architecture would say exactly how to do this, but again, rather arbitrarily, we'll pack our instructions together into 3 bytes each. A consistent length of 3 bytes per instruction makes our code easier for the computer to work with. So we'll reorder some bits and pack on some zeros, and here we go. 12 bytes that tell the computer what to do. Let's take these, load them up into RAM, and tell our computer to start working its magic. Once we've pointed the processor to our instructions in RAM, it'll start executing them in sequence. Since computer division is actually pretty complicated, we'll skip ahead to our add instruction to see how our computer actually does things. The first thing our processor does is decode the instruction, basically undoing the encoding we've just done so the processor understands what we want it to do. It will see the instruction, the destination, the first bit flag, the second bit flag, the first argument, and the second argument. After decoding, the computer knows that we want it to add 4 to R2 and put the result in R2. Mathematical instructions like add will get shipped off to a part of the processor called the arithmetic logic unit, ALU for short, which is designed to handle addition, subtraction, multiplication, division, and the like. An ALU, like everything else in a computer, is a circuit made up of smaller circuits called logic gates. To explain these, we'll need a short digression into logic gates. Fundamentally, a logic gate is a circuit which takes one or more digital inputs and produces one or more digital outputs. Digital here meaning that our logic is binary. Everything operates in either 1 or 0, high or low, power or no power, and nothing in between. Let's denote the inputs A and B and the output Q. Logic gates are defined by something called the truth table, which shows the value of outputs for every combination of inputs. One of the most fundamental logic gates is called an AND gate, a gate which outputs 1 only when both A and B are 1. Next up, there are OR gates, which will output 1 when A and or B are 1. An OR gate is only 0 when both inputs are 0. Similarly, there's an XOR or exclusive OR gate. The important distinction here being that Q is only 1 if either A or B are 1, not if both are 1. And finally in our shortlist we have a NOT gate. This one actually only has one input and one output and just flips the input value. Each logic gate also has a unique symbol that represents it in circuit diagrams. So back to the problem at hand, addition. How do we define a circuit that does addition? Well, let's start with a truth table. 0 plus 0 makes 0, 1 plus 0 makes 1, 0 plus 1 makes 1, and 1 plus 1 makes 2? Okay, something is clearly wrong. To solve this, let's redefine our output Q as S for sum and add another output C for carry. Carry will be 0 for every output less than 2, but when we add 1 plus 1, let's output 0 for sum and 1 for carry to show that the circuit overflowed. Now how do we build this out of logic gates? Let's look at a truth table. Take a good look at S and you can actually see that A, B, and S match the truth table for an exclusive OR gate. So let's put one of those down. Do the same process for A, B, and C and we have the truth table for an AND gate. Let's check to see that everything works now. When A and B are both 0, S and C are both 0. When A is 1 and B is 0, S is 1 and C is 0. When A is 0 and B is 1, same result. And when both A and B are 1, S is 0 and C is 1 since our decimal result is 2. Looks like our addition circuit is ready to go. In actuality, computers use something called a full adder, which takes a carry input as well as an output, but the circuit was a little too complex for this video. I'll leave the truth table as an exercise to the viewer, however, the circuit isn't much more complicated than our basic adder. The key idea behind a full adder is that a bunch of these circuits can be daisy-chained together in sequence to add arbitrarily large numbers, making some pretty big addition circuits. In a similar fashion, take a bunch of these big adders and jam them in a circuit together with some other unique arithmetic circuits and we have our ALU. And as a really quick aside here, Technically, logic gates are made up of even smaller components called transistors, but again, a little too complex for this video. So back to our addition, adding 4 to R2 and putting the result in R2. First, the processor will take the constant value 4 and read the value 6 out of R2 and pipe these both into the ALU, which will use a bunch of adders like we just saw to add the numbers together. And out comes 10. The last thing the processor does for this instruction is take the value it got from the ALU and write it into our destination register, R2. Our other instructions, subtract, multiply, and divide, are done in the exact same way, just using different circuits in the ALU. So now that we know how everything worked, let's put it all together and start from the very beginning. We started with our expression and broke it down step by step into a set of binary operations. We sent the outputs of those binary operations into registers, then we reformatted everything into assembly code, took that code and sent it through an assembler which used the definitions in an instruction set architecture to convert our assembly code into binary which the computer could interpret. Then we put our binary instructions in memory and told the processor to start executing. The processor saw each instruction in sequence and decoded it according to the ISA. The processor executed the instructions, divide 10 by 2 and put the result in R1, multiply 2 by 3 and put the result in R2, add 4 to R2 and put the result in R2, wherein the processor took the instruction, got the arguments and tossed them into the ALU and told it to add. The ALU took the arguments and put them through a bunch of daisy-chained adder circuits made up of logic gates to add them together, each logic gate behaving according to its truth table. The processor took the output and wrote it into our chosen output register. Then the same thing is done with the subtraction instruction and we get our final result. At long last, we know for sure that 4 plus 2 times 3 minus 10 divided by 2 is 5.